This video has been supported by PCBWay. Hey folks, it's time for another episode in my eternal quest for the best 10V DC reference standard. All I need is a portable, stable, low-noise 10V DC source to test and calibrate all of this stuff. Can't be that hard, right? Today we are trying to find out if Analog Devices was successful at overthrowing the undefeated best voltage reference of the last 40 years, and if we benefit from that at all. But first, a quick historic overview to set the mood. In the early 1970s, when the best voltage standards were still saturated mercury batteries, called Western cells, Robert Dobkin and colleagues at National Semiconductor developed a new way of manufacturing nipples. Oh, no, wait, that was a different story. Developed a new way of manufacturing Zener diodes below the surface and within a silicon wafer, thereby mitigating effects from contamination and charges trapped in the oxide layer above. They sprinkled a few more clever ideas on the same die along with this buried Zener diode and called the result LM199. It was a groundbreakingly reliable voltage reference at the time, and it would still outperform most standard parts today. Dobkin and friends later founded Linear Technology and naturally started refining solid-state voltage references even further. In 1983, only 2 years after the incorporation, Carl Nelson and Mark Glanville, and probably many LT colleagues who were not so lucky as to have their initials perpetuated on the die, finished working on the legendary LTZ1000. A super Zener that was so far ahead of its time that it would dominate the ultra-precision market for 40 years or more. In this long time period, the semiconductor industry has grown explosively and seen more innovation than any other field. Yet this relic from the 80s, with no more than 4 devices in its block diagram, remained best in class, virtually unchanged. Until, just recently, someone finally dared to make an update. This someone happens to be Analog Devices, previously Linear's biggest competitor, and now its owner. Why hasn't anybody done this earlier? I suspect 3 reasons. First, these are niche low-volume products. Even if they earn $50 per sale, they will never be as profitable as a battery management IC that will end up in 1 million smartphones. Second, I suspect the original 80s design was already close to what's technically possible within a standard bipolar fabrication process. And third, designing a new part from scratch, even just for a tiny improvement, is not as easy as just plopping 2 transistors, a Zener diode and a heater onto a die, before calling it a tape-out. Here they also have to design structures in 3 dimensions, the doping profiles for those, and a number of additional metal layers. The new ADR1000 from 2017 is not only externally pin-compatible to its predecessor, its die also looks very similar. Superficially we can see a very nice and symmetric coaxial layout, so that the silicon heater rings can cause a very even temperature distribution. Following the metal trace from an annotated bond pad, we can see that there is a significant difference between the cross-section illustration with the central nipple from earlier and the real implementation here. The central nipple in the ADR1000 is not even a part of the Zener diode. It's an emitter of an NPN transistor that is intertwined with the ring-shaped features that form the actual diode. Just like before, the combination of an avalanche-dominated Zener voltage with a positive Tempco and the base emitter voltage of a thermally coupled NPN transistor with a negative Tempco allows a user to create an almost temperature-independent overall voltage by balancing these 2 effects against each other. And if that isn't good enough or too time-consuming for mass production, there is, as always, a method to hold the coarse temperature at a very precise set point above ambient, out of reach of most disturbances. The biggest difference in this new part that we can see with bare eyes is that we have wire bond pads that allow 4-wire sensing of the Zener voltage, a very nice feature for future reuses of this die, but not connected to anything in the currently available TO5 package. The manufacturer's datasheet mentions a few other advantages over LTZ1000, such as improved initial accuracy, and in my opinion, most importantly, lower noise. That alone is enough to make me want to use this part, but I have to say, the immense street cred that LTZ has built in its 40-year lifecycle, and in famous roles such as the foundation of all the legendary voltmeters, cannot simply be inherited to a new part with a similar name. It will have to prove itself on its own to convince the numerous doubters. Personally, I am a doubter of isolation slots. Let me just extend the timeline a little bit further and then we are getting started. In February 2020 I adopted a Fluke multifunction calibrator. That one occasionally wants to commune with external standards. And that's what started this whole project in the first place. I heard the first rumors about ADR1000 later that year, but started planning a naive LTZ1000 based standard in a mu metal can anyway. That's where the mu in the name comes from, even though the thing we are building today doesn't have that anymore. Because in July 2021 I finished that and soon after realized, through comparisons to Fluke 732A, that it wasn't doing all that well. As a consolation or as an aid to build something better, I've been given an early ADR sample, also in July 21 but with an exquisitely rare 2017 date code on the can. Wow, a real collectible first generation part. I had a strong urge to stash it away in my cool parts collection, but I resisted and instead started planning the video you are watching right now, where we are going to benchmark this new part in a universal test board. This is not my high-performance test board, of course. For this one I simply used cheap 1% metal film resistors to assemble the strangely specific datasheet resistor value suggestions. That way I was able to power on our first protagonist right away, allowing it to start working on its initial drift and hopefully have it settled down and mostly stable by the time my real, final, custom-made, hermetically sealed, all-in-one Vishay bulk metal foil resistor network arrives. What a mouthful. Let's just continue to call them golden boys. I wanted to get a head start on the initial drift because it can apparently take over 2000 hours regularly for a part to reach respectably low levels of long-term drift, and possibly even longer than that when operated at a lower temperature. As a matter of fact, independent data for few-year drift just doesn't exist yet for the ADR, so as always it's a bit of a risk being an early adopter. And that's finally all the groundwork done. TLDR so far. I'm building a better 10-volt standard for calibrating voltmeters. For that I would like to use a newly released Zener reference by Analog Devices. But I'm not yet sure if it is as good as they say, so this board will accommodate both the traditional LTZ1000 and the new, possibly better or worse ADR1000. Then we can assemble a few different trim levels for comparison and make an informed decision on what to use in the end. My reference circuit that forces a few milliampere through the Zener diode and its temperature coefficient compensation transistor is almost a carbon copy of the boring datasheet suggestion. What? Carbon? Ew. Let's not take the resistor freedom too far. I only added a generous sprinkle of alternative footprints and jumper links. Those will allow us to use whatever shapes of precision resistors we may have handy, and also to fine-tune some values by adding series parallel resistors after the assembly. These 4 optional TBDs can be populated with a few hundred kiloohm to adjust the amplifier gain ever so slightly and therefore the Zener current. Down here we've got an alternative to the notoriously tricky 13K 1K oven temperature setting voltage divider. In datasheet-based vanilla LTZ circuits, this used to be the most influential part, because a small ratio error could have a large impact on the output voltage. That's why I used to be, and honestly still am, crazy about these gorgeous VHD 200 voltage dividers, which offer the best ratio stability in the industry, pretty much without competition. They are appropriately pricey though and have a long lead time for strange values like 1K 13K. So this Datron WaveTech-inspired technique offers a great cost-effective alternative. Here we are using a monolithic array of 8 equal thin film resistors. Each on their own is nowhere near as good as the aforementioned Vishay foil. But because they are all manufactured equally and thermally coupled by a superbly smooth silicon wafer, one can imagine that they are all going to drift similarly, with temperature, time and other effects like humidity. So if we assemble a functional equivalent of the 13K 1K voltage divider out of these equal resistors, and then something bad happens to all of them, making them drift in the same direction and magnitude approximately, we magically still maintain our ratio. Haha, get ratioed, expensive foil resistors. Now these octal thin film arrays cost $3, $4 or $5 or so per piece, and they are not miracles unfortunately. But by combining this technique with fine-tuning of the Zener temperature coefficient, we can get great results, I'm sure. The optional alternative footprint is here at least for consideration. and it's reconfigurable with jumper links for different oven set points. In the power supply department, we are basically just doing what we have discovered in the extreme isolation video. Check that out if you want to know more about common mode immunity in DC to DC converters. Here I'm using an open loop slew rate limited push-pull driver on the primary mains earth referenced side of a custom-made, Keithley patent circumnavigating ultra-low interwinding capacitance toroidal transformer. Just nod your head, it'll make sense when you see it. I'm preparing 2 redundant DC inputs so that for a battery change or for taking a board out of a chassis, it doesn't have to be powered down and therefore doesn't lose any accuracy. As convenience features, I've added an I2C EEPROM for storing cal values or whatever in, an I2C internal temperature sensor, and a Fluke 732A inspired latching LED that is extinguished if power, and therefore if ppms are lost. The third and final page in this schematic is the output buffer. Its job is to convert the 6 to 7 volt reference voltage to as close as possible to 10 with a fixed gain amplifier. For that I'm using one of the lowest noise auto zero op-amps in the industry, the same one that I used to build my 0.1 to 10 Hz ultra low noise amplifier. Its output is said to be short circuit safe and it could probably deliver a few milliampere without too much degradation of the specs. However, I thought it would be fun to try and match Fluke 732 specifications wherever possible, so I'm aiming for 10 mA of output ampacity. I hope that nobody ever loads their fancy voltage standard that much, but hey, better safe than sorry. After having fine-tuned and compensated the Zener diode temperature coefficient elsewhere, I expect that the gain setting resistors here are our new Achilles heel, the most vulnerable point in the circuit to temperature and long-term drift. As always, you can play the money card and get a VHD200 to defeat this problem. You need a 2K-5K ratio for LTZs. And this is actually another advantage for ADR1000, a much more common 1:2 ratio, to buffer the ADR's output voltage to 10 volt. I propose the same thin film array solution as before, but I'll build more expensive trim levels too, and then we can compare. I'm not currently planning to include a means for trimming the output to 10.0000 exactly. That would be a potential source of error, complexity and cost for the sake of a small aesthetic thing. The op-amp's noise contribution should be nearly insignificant in comparison to that of the reference circuit. But for auto zero, zero drift, choppers or whatever you want to call them, it's not nothing. So I'm adding some optional RC positions for filtering. I'm using a dual analog switch for output protection. It's within the closed loop of the upper op-amp, so it shouldn't have any impact on the circuit performance. The ADG5401F provides ESD protection, and it just opens up when somebody accidentally feeds a voltage up to 60 volt into the output. I'm also pulling low its enable pin when somebody is drawing more than 10 mA to protect the output transistors and to avoid generating excessive heat inside of the enclosure. This ADG part is a bit on the expensive side, so it's optional of course. For the boards, I'm going with 100 by 160 mm outside dimensions, because those fit into standard Eurocard subrack systems, and there are plenty of portable and desktop enclosures available for that format too. Our sponsor PCBWay has recently lowered their prices for many layer boards drastically. So while that is a huge overkill for the complexity of this thing, I'm going to route this on 6 layers, just because it's affordable and there are 2 small technical advantages. One is simply that we are able to spread more large uninterrupted copper polygons across the sensitive area. Those help equalize temperatures across the board and therefore lower unwanted thermocouple voltages. The other advantage of 6 layers is that we essentially get to use star grounding, except for the 5 most important signals instead of only ground, and much more compact and easy to route. The idea of star grounding is that PCB traces have a small but not non-existent resistance. If we were to send our 5 mA Zener current through the same 100 milliohm PCB trace as the heater current or an op-amp power supply return for example, our output voltage could be influenced greatly by variations in those additional currents and by the bad copper resistance temperature coefficient. That's why in applications where it matters, we want to give every current its own path to a central grounding point, or its own exclusive via to a central copper polygon on another layer, so that they don't get in each other's hair. By influencing greatly, I mean a few ppm. That would be huge for what I'm planning. I hope nobody actually believes that I'm some kind of robot-voiced autorouter. I've just been playing back video of me deleting traces in reverse, because in reality it's just a super long, boring process that nobody would want to watch. The only wisdom I could share about this is that for me a 3-step process seems to work best. First, I arrange parts into small functional groups and try to find area for them. Then I connect pads that need connecting within the groups using the thinnest possible traces, just to visualize if a given arrangement is topologically optimal, i.e. needing the least amount of vias. If so, I start maximizing trace thicknesses in step 3. It's not quite free real estate, but why should I have my free copper etched away? Copper good, reps like. It may look a bit chaotic, especially that ghetto in the south, but I think technically it's damn near optimal. The heater transistor and the buffer op-amps can be sources of heat, so I've added these 2 isolation slots between them and the most sensitive components. Overall, we are looking at tiny effects though, because this whole card should consume no more than a watt of power, maybe 1.5 with DC to DC converter inefficiency taken into account. And we are off to PCBWay, where these boards will be lovingly manufactured. From high-quality materials and within the tight tolerances of their standard 6-layer process, as befits the most ambitious DCV standard I've ever attempted. I'm happy to say that this time no extraordinary options such as flex or metal core PCBs are necessary to make this work. I do have a preference for their organic solderability preservative coating lately, because it allows you to admire how much beautiful copper you've got left on your board, without polluting it with foreign metals such as nickel, tin or gold. This coating just disappears without residue on contact with hot solder. In this case, however, I'm willing to make a compromise and accept good old electroless nickel immersion gold, because it is convenient to ground some enclosures with this exposed strip on the side of the board. Anecdotally, I've heard that this ENIG plating makes very little difference in terms of thermal EMFs, so pretty much all of PCBWay's default options are going to work alright. I've used their fast and reliable prototyping services extensively throughout this long project, so much so that they bestowed upon me some wonderful Christmas presents. It kind of reminds me of a brewery sending out an honorary best customer badge to the local alcoholic. Yeah, I went through lots and lots of ideas and revisions before arriving at what I'm presenting today. Such as these octal SMD resistor to dip footprint adapters. I thought I could imitate the expensive all-in-one Vishay foil network that we ordered earlier. By combining individual, high-quality but affordable thin-film resistors, by coupling them thermally and maybe even heating them just slightly above ambient, with a crystal heater circuit on the other side. This might not be the best performer in the end, but I am certain that we will be able to find many great applications for PCBWay's double-sided copper core material in the future. Alright, enough beating around the bush, let's build one already. Around 5 meters to the left of the camera there's already a 19-inch subrack, filled with 4 ADR MUs and 4 battery modules. Those are older board revisions, but they have been running for at least 4 months. This way, I hope I can at least show you the beginnings of insightful long-term statistics and conclusions at the end of the video. However, to not make this story any more convoluted than it already is, let's just pretend that this is number 1. Whoa, 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 no buttered side down jokes today, please. I tried to keep this hand solderable at first, but ultimately failed. If you want to build one, I'd recommend a stencil and paste. The latest version, as of January 23, uses leadless LFCSP packages for the output op-amps. Those have an exposed heat-sinking pad, which is important for the mostly unimportant 10 mA output ampacity requirement. And my favorite integrated temperature sensor, TMP117, would also be very inconvenient to hand solder. Sorry. When using an all-in-one resistor network like a Vishay foil PRND or the copper core SMD thingy, some normally closed jumper links have to be severed, and others have to be bridged on the bottom side of the PCB. I did it this way because I expect this is going to be the least popular option. In terms of leaded components, there is one big electrolytic reservoir cap at the power input. With it, and with the input diodes, you could theoretically operate this thing from low voltage AC. In an emergency, when ppm loss is otherwise imminent. Then there are some leaded film caps for no real reason. They are too small to filter noise in the very, very low frequency range. And they are overkill for everything above 1 Hz. They are also surrounded by relatively low impedance circuitry, so neither leakage current nor dielectric absorption nor microphonics should matter much. If these turn into MLCCs in future versions, you know why. The power transistor is a leaded part because in normal operation it dissipates a lot of heat. The further away from the board we can get it, the better. For post-assembly cleaning I used delicious dichloromethane last time, triggering everybody. This good stuff is a little too good to use on sensitive plastic package ICs, I agree. So this time an altogether different but equally questionable cleaning method. The arch enemy of crystal resonators and aluminium foil. The ultrasonic cleaner. What do you think? Will it harm my precious metal foil resistors? I don't think so, because there's always a ceramic backing and no direct liquid contact for the foils. Uh-oh, that's not true for the predetermined overpressure breaking point in electrolytic caps. But immediately after cleaning, it doesn't look like we've lost any ppms. Still, we may have caused subtle damage to plastic encapsulations or the hermetic ADR seals. So I'll be watching number 13 closely before subjecting any other boards to ultrasound cleaning. Winding the DC to DC transformer is easiest with a twisted pair of enameled copper wire. To avoid the Keithley patent that protects shielded windings, I'm just going to rely on distance, keeping the interwinding and core capacitances low. These amorphous cores that allow us to get by with so few windings usually come with a plastic encapsulation of their own. This acts as a basic spacer and guarantees good common mode immunity. But to be worthy of the title Extreme Isolation, I'm adding another spacer, made from FR4 substrate. When aiming for a 12-volt input, I'd recommend a 5:6 or 5:7 turn ratio, so that you get a bit of headroom on the secondary side for voltage regulation, and to allow the output buffers to push enough current through any RC filters. By wrapping a twisted pair around the toroidal core, you are essentially forming two separate windings. To allow the push-pull driver to do its job, you can take two opposing ends, one of each winding, and connect those to the positive input voltage at the central terminal. The two remaining wire ends are connected to the appropriate pins on the LT3439 driver. Ultimately, it will allow current to flow through these alternatingly, causing an alternating magnetic flux in the core. That's a lot of effort and costly materials for a bit of isolation. An off-the-shelf DC to DC converter might be worth considering if your application doesn't need extreme isolation. And now, the stars of the show. I have two of these custom-made Model 1445 resistor networks. As I said, the first one has been installed in ADR1000 in March 22, together with the antique first-generation ADR1000, so that we have lots of data available now. The other one, a keen observer might be able to tell, is not yet installed and still available for fondling. Don't worry, I haven't murdered that. This is a broken, similar part that somebody has donated a while ago. It shows how these hermetic packages are filled by a number of discrete bulk metal foil resistor chips. These start out as basically short circuits until a Vishay technician manually fondles them to practically any custom resistance value, up to 33 kilo-ohm in bulk metal foil technology, and up to half a mega-ohm as slightly less awesome thin film, by opening some of those numbered bridges on the left according to their software. When compared to ordinary everyday resistors, such a service isn't cheap, but considering that this is the best mass-produced resistor technology in the world, available in custom values and custom circuit configurations, the pricing is not at all absurd. Hold up, 1 second. I ordered these all-in-one resistor networks exactly as per ADR1000 datasheet recommendation, meaning 1K 13K sets the oven set point, 95.3 ohm sets the Zener current, and 61.9K biases each the temperature sensor and the reference circuit. I went with these lame default values to configure the references exactly the way they are meant to be, and to rule out negative influences from the environment, or my own non-standard implementations while testing their basic parameters. Not that I would mistrust a billion-dollar company's datasheet specs, oh no sir, not at all. I just think that there is not enough independent ADR data out there yet. Speaking of ADRs, of course we can't get meaningful data with a sample size of 1, so I got a few more specimens to test. Availability of this part has been problematic so far. It might be wrong or no longer up to date, but I think ADI's official statement was that this isn't a full open market released component, because the team in charge of this project doesn't have the resources to offer long-term customer support, educated design engineers to provide implementation advice in the ADI forums, or capacity to handle the bureaucracy of getting these out to all the international distributors. Surely a launch in the middle of an international supply chain crisis also doesn't help. Whatever it may be, I'm happy that at least for a while, these were available to everyone in smallish quantities through direct manufacturer distribution. After asking Analog for another quote in January 23, I only got a default email back pointing me towards their distributors. So I guess the direct distribution days are over for now. Good thing I have a few left. I'm going to assign them internal numbers on the off chance that we can correlate batch numbers and date codes and initial accuracy, burn-in behavior or noise or something. For this board with the all-in-one network, I'm going to select the best ADR out of my trove of factory new parts, based on proximity of the buffered output to 10 volt. Again, this is only aesthetics. As long as the reference lands somewhere between 9 and 11 volt, it's going to do the job for artifact calibrations. ADR number 9 with a 2022 date code is only around -10 ppm off of 10 volt exactly. The datasheet predicts a +5 ppm initial drift, so if we are lucky this one might end up very close to 10.0 volt. While we are here, let's try the overcurrent output and the accidental input protection functionality, powered by ADG5401F. This is a pretty pricey module after all, and to err is human. Is that not correct, fellow humans? Yeah, that's looking great so far. We can draw a couple of milliamps without the output voltage changing significantly. At 9 mA the output switches are opened and the SMU can't draw any more current, even when it goes all the way to its 21 volt compliance setting. We can sink milliamperes too, but the circuit is not designed for that. A part that isn't particularly well heat-sunk has to do the power dissipating in this case. What the input protection is really meant for is an emergency disconnect when somebody accidentally connects a lab bench power supply, a charged capacitor, or a voltage calibrator that is still outputting something. That causes a lot of milliamps to flow, but only for a fraction of a second until the output protection notices it and opens up. This open switch can withstand 60 volt. It should also be able to handle 2 kV of ESD, but I'm too scared to zap this potentially golden prototype. Maybe later, if we identify a drifter that needs to be taught a lesson. There are plenty of housing options for our PCB format, most prominently these Eurorack-compatible plug-in cassette modules that I learned to love in the CERN ADC project. This board, my number 3, has an LTZ1000A under the hood, and it's based on an older, simpler PCB revision. I imagine having a few LTZs in the mix can be a kind of old versus new sanity check. There are much simpler housing options too that don't require you to commit to a subrack. For example, these single Hammond desktop enclosures, for which I've prepared some custom front and rear panels that you can order from PCBWay as aluminium PCBs. Careful though, the cutouts in the front panel are prepared for unusual binding posts. If you want to use Pomona 3770 for example, you've got to change them slightly. I even found some adorable press-fit micro light pipes for the uninterrupted power and the status LED. I've prepared the back panel with a mini DIN connector, primarily for reading and writing the EEPROM and the temperature sensor. It could also be repurposed for 4-wire Kelvin sensing, but not without detaching the sense leads from the front connectors. And there are also risky floating ground and VCC pins, with which one could power the reference circuit only, bypassing the DC to DC converter, i.e. for hot shipping references with minimum power consumption, 400 milliwatt or so. Some pure copper bling for the output connectors is nice but optional, to be honest. My rack mount units all have soldered connections and they are doing just fine. Everything else should line up perfectly, and that's another box done and ready for observation. Let's build a lot more, one of each flavor at least. Stencil, solder paste, passives. Oh no, what was I thinking? That joke was not worth this much trouble. Molten sand with impurities, reflow, and some leaded components to taste. This one is going to be the monolithic resistor array flavor, with temperature coefficient fine-tuning. The default datasheet implementations of LTZ and ADR rely on the heater circuit to keep the reference at the same temperature forever, thereby making the Zener voltage temperature coefficient irrelevant. That works very well if a sufficiently stable oven setting voltage divider is used. The VREF in 3458A multimeters and my two ADR Muse with Vishay all-in-one networks work this way. However, that sufficiently stable voltage divider is always expensive and hard to find. So now we are going to try to flatten out this TC curve and to position the oven set point directly at the apex, so that small temperature variations have an infinitesimal impact on the output voltage, ultimately allowing us to get by with cheaper resistors. And this is where we converge with another old side quest, the desktop temperature sweeper based on Arroyo tech source. This allows me to evenly heat the entire board as if it was experiencing ambient temperature changes. That matters because not only the Zener reference has a temperature coefficient, the 10-volt gain stage does too, and there are probably many more small Tempco contributors on the board. By including everything into this adjustment, I hope to compensate for the sum of all the little effects, down to the Kovar copper thermocouple voltages, and end up with a nearly temperature-independent 10-volt output. Also, this is the only scenario ever where I could imagine observing PPMs through Vago connectors. To start with, the board is mostly configured as per ADR datasheet recommendation again. Only the heater is disabled because that is what we want to control externally. I'm going to monitor the overall output voltage while sweeping the chamber temperature from 20 to 70 degrees Celsius. We are seeing a slight negative Tempco and a kink in the voltage curve at around 62 Celsius. The negative Tempco over the whole temperature range means that the standard resistor configuration is not optimal. The kink in the voltage curve, I think, is a parasitic semiconductor effect that occurs when the disabled but still present heater op-amp transitions from on to off. Makes sense with my oven setting voltage divider forming a roughly 12K 1K equivalent. To make the TC curve bend to my will, I can either modify the pin 4 Zener anode resistor or the pin 5 Q1 collector resistor. For LTZ we had to add an extra 20 ohm resistor above pin 3 to bring the TC adjustment range within reach of optimal. The new part comes pre-adjusted a bit better, so that is no longer necessary. In this sequence of temperature sweeps I've lowered R2 from 60 kilo ohm in 10K steps until at 30K, suddenly, the mythical TC peak made its first appearance. It's now located at roughly 22 Celsius, which would be okay for a low-power, unheated, room temperature reference. If the energy prices are getting any worse, we might have to explore such options. But this time I would like the TC peak and the oven set point to coincide somewhere between 40 and 60 Celsius. We can also see how the line is starting to become a bit bumpy. That is voltmeter noise, and it's a great sign that the curve is very flat, i.e. we've already improved the Tempco a lot. But I'll continue to lower the pin 5 resistor in baby steps now. It's a tedious task with lots of commuting between the soldering station and the test gear bench. And it looks like it's slightly different from part to part. So I can understand that OEMs generally prefer using an expensive temperature setting voltage divider, rather than paying for the man hours to make these finicky adjustments. On a smaller scale though, if one has an acute need for a low-cost voltage standard, it seems totally possible to optimize these to near perfection. This one is nearly there, with the flattest TC neighborhood at around 47 Celsius, and the oven set point indicating kink in the curve at around 55. It's possible to go much hotter than that if high ambient temperatures are expected, or if a reference is meant to be installed inside of a warm enclosure of another piece of equipment. However, a high oven set point comes with elevated long-term drift, so keeping it as cool as possible is desirable. And here we are after one more micro adjustment. The blue curve is bell-shaped normally. The sudden change in direction as the heater set point approaches, I think occurs only with the heater control loop open. It shows how close our alignment is, and it should disappear as we finally reconnect the proper built-in heater. Here's my intermediate result. I've wired the temperature setting resistor network RN201 in such a way that it forms an equivalent of an 11K 1K voltage divider. And then I've added an external resistor in the R202 position to give it a small nudge upwards. Normally, adding an external trim part has a good chance of ruining the big advantage of these monolithic networks. But the influence of this one is small, and it should bring us in the flat TC neighborhood, so it's even smaller. The aforementioned pin 4 anode and pin 5 collector resistances, with which I have configured the overall Tempco, were present in the final adjustment step, so their own Tempcos are accounted for and compensated. This is an automatic consequence of the process, and it would have worked just as nicely with a low-quality carbon resistor, for example. Unfortunately, they don't only influence the thermal response of the reference. A change in their absolute value also has an attenuated impact on the 10-volt output. For example, a 1% resistance change could cause a 1 ppm voltage change. So these two positions don't necessarily need low Tempco resistors. But low long-term drift, found for example in precision wire wounds, would be advantageous here. I went with plastic molded Vishay foil in this unit, which is probably an overkill. But while evaluating the ADR1000 and this whole project in general, I didn't want to risk confusion from some unknown resistance drift. Here I'm supergluing some plastic caps over the ADR, so that it isn't influenced by air movements that its own heater causes. Models for these caps should already be uploaded in the GitHub repo. Even decent quality, newly released in 2022 MSLA machines still can't handle a simple closed cup shape. That's why they are in two pieces in case you were wondering. Anyway, this ADR-mu, I'm calling it number 7, is nearly ready. Let's reconnect its own heater and test how well it does. I've placed it into the temperature chamber again for another slow sweep through all acceptable lab temperatures. I've moved the chamber with its strong forced air cooling some distance away from the voltmeters, so that they aren't influenced by the exhaust. First impression, positive. The 5th digit after the decimal point, the 6, represents the ppms, and it's stable. So are the hundreds of ppbs, and only the least significant digit, the tens of ppbs, is moving visibly. Very nice for an only just assembled reference. Over the course of 1 hour, so that every last little component has enough time to acclimate, I'm sweeping the board from 15 to 35 degrees Celsius. That's a much larger range than I would expect in any kind of halfway serious lab situation. But ADR-mu number 7 can obviously handle it. After its first Tempco fine-tuning, it has roughly plus 0.02 ppm per Kelvin remaining. That's 20 parts per billion FYI. We got lucky in this case. In previous assemblies, at this point I would have performed another adjustment to lower the remaining Tempco through adjustment of these optional resistors. In this case I won't. This is plenty good already, and every additional resistor comes with a risk of long-term drift in tow. I'm giving it the same amount of time to go back down to 15 Celsius. If we land on exactly the same output voltage where we started, I think that's called good retracing. However, we do in fact land 200 parts per billion lower. I don't think that's a hysteresis effect from thermal shock. It's more likely that it has something to do with the reference only just having been turned on a few hours ago. I also don't know what the deal is with those downward spikes. I hope it's just faulty makeshift wiring in the thermal chamber, and not a case of the popcorn noise disease in this lucky reference. We'll find out. And that almost brings us to the final chapter in this long video. I only want to touch one more small topic before that. Oh my god, is that a portable power station? No, maybe, but what I meant was accelerated aging or burn-in of new parts. This is a bit of a snake-oily topic that has been discussed a million times over with no clear conclusions. I won't be able to deliver those either, but I can show you what I've done to two of my specimens prior to installation. In one of my test boards, the one with a copper core SMD adapter thingy that didn't work very well coincidentally, I've disabled the heater and installed a TO5 socket for quickly changing references. I've 3D printed this holder so that I can position factory new references on Miniware's MHP30 miniature reflow hotplate. I'm feeding the board 12 volt through Miniware's USB powered adjustable power supply, so that it burns the normal 5 mA or so Zener current in the new, soon-to-be aged reference. Throughout this 1 week bake and burn process, the hotplate keeps the part at a cozy 140 degrees Celsius. This is supposed to relieve initial stresses in the epoxy die attach. And I've also heard it said that it can help release trapped charges from the usually non-conductive silicon regions. The former, I believe without a moment's hesitation, the trapped charges not so much. But what do I know? Let's look at the results of all my ADR mules, pre-cooked or not. First of all, I can guarantee none of these results. The only legitimate calibration for which I have a certificate is Keysight 3458A, and that is well over a year old now. I may have appropriated some surreptitious under-the-counter PPMs, but only once during my recorded history. Theoretically, every participant in this 4-month cross-comparison could be drifting in the same direction and magnitude, and I would have no way of noticing it. Practically though, I have so many participants now that is unlikely. Kind of the reason why I built this quad subrack. ADRMU1 is the 2017 date code ADR1000 with which we started this whole journey. It is set up in the oven temperature dominated datasheet default configuration, but it uses the most stable foil resistors in a hermetic package, which is why it should still be very, very good. This part has been powered on for over a year before this measurement started. In a direct comparison to the voltage reference in 3458A, we can kind of still see a gentle downwards trend, in the order of roughly 0.1 ppm per month. That would be more than the 0.5 ppm per year that the datasheet promises. But wait, it's not pitchfork time just yet. The voltage references in 3458As are actually not that great, especially not when they are still running at the factory default 90 degrees C set point. This is what can happen when you tinker with solar energy and accidentally turn off a meter for a few hours. The LTZ in there suddenly lost over 70 degrees Celsius and jumped an entire ppm in response. That is also kind of why I built this quad subrack, why I'm trying to keep the oven temperatures low, why every reference module is supported by a dedicated UPS that can keep it alive for 24 hours, and why every ADRMU has an uninterrupted power indicator LED now. Number 2 uses an LTZ1000A and also a few $100s worth of Vishay bulk metal foil. This thing is pretty much pimped out as far as it was possible in this early board revision. There's a VHD 200 each for the oven temperature target and the 7 to 10 volt gain. Every other resistor that matters is also precision foil, and there's temperature coefficient fine-tuning. Strange. According to 3458A, number 2 also had this downward trend over the last 4 months. All of these near-daily measurements are preceded by an ACAL, so the voltmeter's front-end and ADC drifts are eliminated. These are pure discrepancies between silicon voltage references. Now, with 2 ADRMUs running simultaneously, we can pull out the advanced mathematics and look at only the difference between 1 and 2. Taking 3458A out of the equation reveals that 1 and 2 exhibit very similar drift behavior. The ADR in number 1 and the LTZ in number 2 are almost never more than 0.2 ppm apart, and there is no trend visible yet. But whom to believe? The best voltmeter ever from the legendary HP engineers, or some YouTube idiot's creation pieced together from EEV Block forum lore? Well, I have a few more arguments which you might want to consider before making up your mind. Number 3 is also based on LTZ1000, but resistor-wise it is the opposite of number 2. It's the cheapest resistor trim level possible. It uses those monolithic thin film arrays for the oven set point, for the 10 volt buffer, and for the Zener current. Only the pin 5 collector resistor is a precision foil, a salvaged low quality S102 model that I had lying around. In total, the resistors in here should be worth 20 or 30 USD tops. Almost an order of magnitude less than the ones in 1 or 2. And the entire assembly costs maybe 2% of the price of a new Fluke 732C. Yet, thanks to the Tempco fine-tuning, it is working brilliantly. So far. Those TDP or NOMC arrays give us outstanding ratio stability for a low cost. But their plastic molded IC packages are suspected of growing and shrinking with absorbed air humidity, which might make them drift. So far though, over the last 4 months, this low-cost model was actually better than Fluke's finest DCV standard datasheet specification, assuming 1 and 2 to be stable. In practice, a Fluke standard is usually doing better than its datasheet guarantees. But I too am only just getting started. Number 4 in the subrack is based on ADR1000, but it's a novel implementation, unlike any of the other modules. It has great potential for being the easiest method ever for getting overniced Ultra Zener performance into any circuit. But so far it's only mediocre, unfortunately. I'm going to tweak and watch it a bit more, and then I'll make a separate video about number 4. One of my intentions with this quad subrack is using it as a mobile transfer standard, to share PPMs with friends. So as a first test I took it with me on an all-day road trip in a 15° C trunk. Not to any source or recipient of PPMs this time, just to see if it maintains integrity. Well, the good news is that nothing broke and the batteries still had plenty of juice 7 hours later. And we didn't experience any long-lasting changes. But it took hours for everyone to recover from this mission, probably because only 2 of the reference modules have received the Tempco treatment, and the heavy metal enclosure took a long time to come back from outside to room temperature. A Fluke standard would handle this much better, because it overnizes everything, the Zener and all the important resistors. Number 9 is the proud owner of the second golden Vishay network. It's just like number 1, except here I'm tracking the initial drift of a factory new ADR1000, without any pre-cooking prior to the first power on. I want to know if it moves roughly plus 5 ppm in the first 3 kilo-hours of its life. And then no more than half a ppm per year, as is the datasheet prediction. The results should be representative because we are using luxury resistors and no non-standard Tempco fine-tuning. But I'm going to have to get an external, reliable calibration to give meaning to my relative results. I am risking making a dent in my previously nice and smooth statistics by powering down and showing the insides of each module. But since none of these boxes currently maintain valuable, traceable PPMs anyway, it's a risk worth taking, I think. This one is called 107 for a reason that I forgot. It's an ADR, a bit older than the last one, no artificial burn-in, and it's equipped with mid-range resistors and Tempco fine-tuning. It's nowhere near 3000 hours old yet, but we can see very nicely how it had an initial 4 ppm drift, and how it's hopefully beginning to slow down somewhere around here now. This flavor, based on 2 thin film networks and 2 foil resistors, I expect is going to have a good balance of stability and cost. There are no risky, low-quality resistors in influential positions, and we are also not going overboard with hermetic Vishay foil in positions whose influence is negligible anyway. I've calculated a rough BOM cost estimate for this one in January 23. With the voltage reference itself, mechanical parts, connectors, PCBs, the inductor core and everything included, it's around 370 USD. The 2 parts that I've pre-cooked for a week before installation are actually well on their way to becoming the worst initial drifters out of the lot. Maybe there was relaxation of the die attach or some other arcane effect. We're going to have to wait and see how this develops, but for now I wouldn't recommend it. I've got one more board here with a jumper link that raises the oven target temperature significantly. This could be a kind of in situ burn-in option. No idea yet if this has any advantages. The board is called number 12 if you want to follow its statistics. I think I'm going to assemble even more, and by recording everybody's resistor configurations, I think we'll find the optimal recipe through automatic periodic measurements and comparisons. By the time this video goes live, there should already be some new data in these IPython notebooks in the GitHub repo. In my 2 parts that are over 3000 hours old now, I'm not seeing datasheet violating behavior, and therefore no juicy clickbaity scandal. Based on the small sample size, I'd have to pronounce this an acceptable LTZ successor at least. But does ADR have a chance at being better than its predecessor? In the absence of massive, obvious differences, it seems like that has to be decided based on noise performance. Sir, any comment on this matter? I still have my low noise amplifier and 0.1 to 10 Hz bandpass filter, but even after times 10,000 amplification, the expected noise signal is only going to be 9 mV peak to peak. Such a small effect could nearly hide in the noise floor of a normal oscilloscope. Luckily, we have a special oscilloscope at our disposal. The new Rohde & Schwarz MX04, one of, if not the lowest noise oscilloscope in its class. In its most sensitive range, it can achieve 50 microvolt RMS noise, among many other great qualities which deserve a separate video. I could have also added another times 10 gain stage in my preamp, but where's the fun in that? First of all, I've made some small subtle changes to my LNA. A small bodge here to make it more accurate, and some new capacitors there, with less dielectric absorption to make it faster between testing different references. Inconspicuous as these changes may be, they have the potential to alter the amplifier's frequency response gravely. So let's quickly verify it, lest we pass judgment in the LTZ versus ADR case, based on faulty measurements. The MX04 has a frequency response analysis app on board, which can use one of its two arbitrary waveform generators to sweep through a frequency range, while one of the oscilloscope channels measures the response of a two-port device. Unfortunately, it refuses to start a sweep any lower than 10 Hz, whereas I would be interested in a 0.05 to 15 or thereabouts range. Oh well, not a problem. Since this instrument is VXI capable, it couldn't be easier to interface with it programmatically, over Ethernet for example, and to set up such a sweep manually. I'll link my Python script in the description below. It should also work for many other Rohde & Schwarz scopes. It tests frequency points on a log scale, because the very low frequencies where we expect the beginnings of 1/f noise and the quality of our 0.1 Hz high-pass filter are much more impactful than the 10 Hz side of things. The script puts out a CSV file with peak-to-peak measurements per frequency point, which we can then display and interpret elsewhere. Looks like a healthy preamp to me. The bandpass quality factor leaves a lot to be desired, but that's for another day. So we are ready for some voltage reference noise measurements. Based on the 0.9 microvolt peak-to-peak datasheet spec, after the ADR 10 volt buffer gain and the times 10,000 preamp, I'm expecting 13.5 millivolt peak-to-peak on the scope screen typically. I'm analyzing around 10 merciless 100-second captures per ADR-based box. I'm interested in peak-to-peak measurements for comparability with the ADR1000 datasheet, and RMS measurements for comparability with Fluke 732 voltage standard datasheets. And that is looking good for all parties involved. It should be said that neither LTZ nor ADR are anywhere close to being the world's lowest noise Zener reference. These guys are aimed primarily at low Tempco and low drift. Within reason, their low frequency noise performance can be tweaked through Zener current and heater temperature. But for today's participants, I didn't do anything unusual with respect to noise performance. I only have two LTZ-based standards in the comparison for now. Number 2 with 1.6 microvolt peak-to-peak is well behaved, just below the datasheet-based expectation. Number 3, the one with the cheapest resistors possible, is a little bit louder, but perfectly acceptable too. ADR-based rack mount unit number 4, which I didn't want to reveal earlier, on grounds of being novel and cool but not yet working satisfactory, turns out to likely suffer from popcorn, aka burst noise. Sad but still usable, and repairable if I get another VREF. My serial number 1, the one with the rare 2017 datecode ADR, is doing well with lower noise than both LTZs, but a smidge more than the datasheet 0.9 microvolt times 1.5 times 10,000 expectation. Number 9's overall 1.22 microvolt peak-to-peak noise suggests an unbuffered Zener noise lower than 0.9 microvolt. In fact, this makes it the lowest 0.1 to 10 Hz noise Zener I've ever tested on the channel. A short-lived glory because number 9 gets to hand that title right over. to number 7, who's even better than that. Yeah, sorry, didn't mean to bore you to death today. I've got many more statistics, hopefully in a more digestible form in the GitHub repo. And I'll try to keep that up to date regularly. In conclusion, LTZ1000 and ADR1000 are very similar. The new part has a few small advantages such as a tighter initial accuracy and needing a more readily available 1:2 resistance ratio for 10-volt buffering. And there is one big advantage, lower noise, which I've just confirmed. It's cause for concern that multiple independent sources report excessively long initial settling times. Personally, I'm only seeing that on the parts that I've tried to pre-cook at 140 Celsius for a week. My untreated ADRs reach a plateau after a week or two. I don't know yet if that's their final destination, but I can't detect any long-term drift in my 2 very old parts. So my final verdict, analog devices, ADR1000, good. But you can't buy it at the moment, so LTZ1000 also good. My ADR-Mu board supports both parts, and you can get it conveniently in PCBWay's Community Projects Hub. If you manage to fine-tune away the overall temperature coefficient, you can DIY a world-class DC voltage standard, the likes of which an established brand would charge $10,000 for. Damn, how did I manage to fill an hour with something that can be compressed into a few second summary? Thank you for watching. Okay, back to portable power stations.